Yeah, Pavana, you can go ahead and start.
Good morning, everybody. My name is Pavana Prakash, and I'm a student of Dr. Miaopan. And today I will be presenting a paper that was recently accepted at the ICML conference, and it's titled Federated Learning Under Arbitrary Communication Patterns. The authors are from Indiana University and Amazon. Here's the brief outline of today's presentation. First, I speak about some motivation and introduction. Then I will talk about the main idea of this paper, which is called the asynchronous communication. Then I will speak of some theoretical analysis provided by the paper, then some experiments, and then finally I will conclude the paper. First, I'll talk about the introduction of federated learning. We know that federated learning is a distributed machine learning setting, which mainly aims to collaboratively train a model under the orchestration of a central server. And federated learning is applicable in both kind of scenarios where you have cross-device settings, where each device can be a mobile edge device, which may have small quantities of data, or it can be a large cross-silo settings where each client brings its own large quantities of data. These things have enabled federated learning to be applicable in a broad range of applications, such as the smart healthcare systems or the mobile augmented reality. Some details about federated learning. Here in federated learning, we have several devices participating and they have their own data sets. And they are the data owners, and the data is not shared with the central server or any other clients in the learning process. There is local training that is performed on the clients, and the model updates alone are sent to the aggregation server, where all the updates received from each participating client is aggregated. And this aggregated model update, the global model updated model is sent back to all the clients participating in that particular given round. So you can imagine that the goal here in federated learning is basically to minimize the objective function f of x, where f of x is the global model function, which is nothing but the summated average of the individual local functions. Fi of x stands for the local functions of every participating device. Here, through the local training, we know we can talk about the local SGD, the stochastic gradient descent, the most popularly used method for doing the local training in federated learning is the local SGD. Here, we allow every client model to evolve locally on each machine independently from each other, and only the sequences of the model update is averaged once per several iterations. This is the basic picture of how federated learning works. So the motivation for this paper is that there are certain challenges that federated learning brings in. First is the communication. So communication can become a critical bottleneck in federated learning because federated networks are potentially comprised of a very massive number of devices, and the communication in the network can become a little bit slower if you have to compare it with the local computation by many orders of magnitude. And the second challenge would be the non-IID. So the devices frequently generate and collect data in a varied manner. For example, if you have mobile phone users and you are doing a keyboard prediction or some language model training on your phones, then we know that every user uses the languages differently. So the next word prediction task can have data which is very varied, which comes from every users can be very different. So this means that the training data are non-identically distributed, which means that the local devices data cannot be regarded as samples drawn from the overall distribution. And the third challenge would be the client availability. So the federated learning server usually doesn't have any control of the participation of the user's devices. For example, you have a round, in one given round, you may have 100 clients participating, and maybe by the time the next training iteration comes by, some clients may lose the Wi-Fi access, or they may move, and they may not have very strong signal, or maybe the device gets powered off because of battery constraints. So there could be several reasons why, because the participants may not participate in every round consistently. So they can be users dropping off, they may be users joining in newly in other rounds. So this client availability is another challenge where the server doesn't really have a control over it. So talking about the client availability, we know that federated learning, as I just explained, deals with synchronization with the server. After a few iterations, every local device sends its update to the server. So they get synchronized with the server and they get aggregated. So during the synchronization process, we know that the communication of model updates happens periodically, or it's usually demanded by the server. And in case of very popular algorithms like federated averaging, the server selects a random subset of clients, and the synchronization with the server happens from those particular clients alone. But as we just saw, this may not be practical because if the server selects a subset of users, the user may not be available for training during that round at all. So the synchronization also becomes another challenge. So keeping these in mind, this paper talks about the arbitrary communication patterns, where they first assume that all the clients evolve at the same rate. So the local training happens amongst everybody almost synchronously. And we set the number of local steps that they take or the number of local iterations for the local training to be the same for all the devices. So they assume that there is a global clock, like many asynchronous papers assume that there is some global clock. And according to that, every client will try to do the training within that kind of a deadline. So all the local iterations are synchronous. But when it comes to the communication part, this paper assumes that the model might have an asynchronous kind of a scenario where the clients communicate at arbitrary times with the server, which is decided by the individual client. When the client wants to join in, when he has enough resources, when he's able to participate, is when he's going to communicate. But the computation is assumed to be synchronous. And another thing that this paper imposes is they assume that there is some delta, some number of rounds that they expect that all the participants may or may not join for training in every round, but there is some delta number of rounds within which all the devices participate at least once for the training. So this is one assumption. And they show through the experiments and theoretically that the clients can communicate much less frequently, but still they'll be able to achieve the same convergence, like how the synchronous setting of federated learning works. So this is the brief idea of what this paper tries to target. If I were to compare this arbitrary communication or the asynchronous communication with the very popular algorithm federated averaging, in federated averaging, the main assumption is that the server gets access to a subset of clients. And in case the clients are not available for training for any given round, then these assumptions get violated. And also there is a main issue is the straggler issues, that some devices may be slower for local training computation, may be much slower compared to the other ones. So so the server has to wait for the model updates to come from all the clients. So this can lead to the straggler issues. And the other thing, some of the papers try to target to solve the straggler issues, they try to do oversampling. But oversampling the user devices leads to construction of a bias set at the server, because the more powerful clients are selected at every round, so the main set that is built at the server becomes very biased. So this also becomes a small disadvantage. And also, if in certain rounds only a very small set of clients communicate, then the convergence rate may not be very good. And given that the data would be non-IID, different data distribution among all the clients, if some of the clients do not communicate, then finding a common minimizer for the global objective may become a little difficult. So these are the other problems of the very popular federated averaging algorithm. So keeping these things in mind, this paper proposes a very simple idea. It follows the federated averaging with just a couple of changes. So let me briefly introduce the algorithm here. On the server side, we have certain notations here. Gamma is the step size used by every client. The capital T would be the number of communication rounds, the total number of rounds that would happen between the server and the clients. X0, let's say, would be the starting point for any client to start the training. And CT, this is the main part of this paper. CT is a set of clients which communicate at a given iteration. So this subset would be that, like I was explaining, you have a delta value, like certain number of rounds, and then you have the global clock. So within the global clock, whoever client participates and sends the model updates to the server, they alone will be considered for training in that round. So those clients come under this subset of CT, set of CT. So on the server side, the communication happens this way. Let's say that the local training was finished on the local clients, and the local clients sent the update to the server. So what happens on the server side during then is the server receives a delta T plus 1. I is the number of clients over here, each client over here. So the server would receive the update from individual clients, whoever is participating in that round. Then it tries to aggregate it and produce the model update XT plus 1. So for producing this XT plus 1, what they do is The server only collects the sees what is the latest parameter vectors of all the clients currently available on the server, and it averages that. So how does it know which are the latest updates and which are not? So what it does is usually after aggregation, the server updates the global parameter vector xt+1, like we just see over here. And it also maintains another parameter called the YTI per client. So in any round T, whichever client I sends the update to it, the server updates that into YTI. So it made this YTI always has the latest fresh copy of that given client. So it updates the YTI every time whichever client sends in whichever iteration, because it is asynchronous. First it updates this, then it waits and sees, and then ultimately all the clients who sent the updates to it, whichever belongs to the CT+1, who their updates will be aggregated, and then the xt+1 will be computed, and the xt+1 will be sent to only those clients who took part in that particular training round. So this way, all the clients who communicate with the server in the pre-specified global clock time window will form the set CT+1. And this is one difference compared to the normal federated averaging. So this was on the server side. Let me briefly.
So can I ask a question here?
Sure.
So the only difference is that the number of, the set of active clients in each iteration T here, right?
Yes.
So how do they choose the CT here? They just rely on each client to, upload their model update. So it's more like random, or, in fact, averaging, the CT is more like a random sampling, right? Now the CT looks like it's more like each client, you just feel free to run tau iterations, and then whenever you are ready, you just send your update to the server, and then the server will do an aggregate. So how does the server set the window? What does that mean here? I don't get the point here. So what is CT here? How do they choose CT?
Okay, I get your question. So what usually federated averaging or the related federated learning algorithms do is similarly like what you said. They do some kind of a sampling to select a few users for that round. So that is what CT would be in other algorithm case. But when it comes to this, the server has no control that which client may or may not participate in that round. So we are not going to do the sampling at all. Instead, they use this kind of a global clock time. This paper does not explain on what basis they choose this global clock time. I try to look up some related papers, but they just say that this is some pre-specified global clock time. So they just set this on the server, and then the server waits only until this time, this pre-defined time. And whichever client sends the update until then, it only aggregates those many clients. So that will form the set CT+1. So the CT+1 is dynamic per round. So whoever sends within the deadline that I set, they become the CT+1. And yeah, go ahead.
So you mean the pre-specified global clock time is more like, for example, every hour or every 5 minutes, I will just wait for 5 minutes to see which client send their mode update to me, and I will aggregate the mode update. So the CT here will be a random, right? Random set.
Exactly. Yeah, that's exactly.
So for the random set, so they propose this algorithm. Then what they do is to analyze the performance of this algorithm, or do they do some control here? So it's more like you can do it in this way, right? So you say, well, I just wait for 5 minutes to see which client will participate, and then you just analyze them. You don't do anything else, or I don't know what's their contribution here. Their contribution, meaning this is not a new algorithm. Looks like it's just like I want to analyze the impact of heterogeneity on my performance, right? I didn't see.
No, you can finish. Go ahead, please.
Oh yeah. I'm kind of. I just want to know. So what's their main technical contribution in this paper?
Okay. So their main technical contribution is that one is the pre-specified global clock time is what they set, and they say that between the the gap between the two updates sent by one particular client, they mark it by delta. So this is, they said that this every client has to participate at least once in this kind of threshold, in this delta kind of rounds, and they give an upper bound for this delta, and they show that this delta becomes really important. And if you have an upper bound for this, and if you give a certain value to this delta, then you are able to achieve rates which are almost same as the synchronous model, but by reducing the communication by a lot of extent.
So do they control the, for example, the length of each global clock period?
Yes, they give a theorem to calculate this maximum gap between the rounds for both the convex and the non-convex scenarios in different kind of settings. You can use the theorem to find this delta.
Okay.
And by setting that, yeah, you will be able to solve the communication problem to a great extent.
So I want to follow up the Dr. Guo's question. So this
Mhm.
delta is related to the global clock time you set up, right?
It is more dependent on the number of total rounds you have and the number of clients who are participating. The global clock time, they do not show it theoretically. They just say that it can be any random number, but they don't have the time, but they use something like the last number of rounds used in the theoretical proof. Instead of the time in seconds, they used like number of rounds.
But I think intuitively, the delta should be related to the global clock time or whatever you call it.
Mm-hmm.
But again, I want to second Dr. Guo's comments. I think the global clock time or whatever, it's just time threshold, right? That's not new. Even in our own paper, I think in one of Jiahao's paper, try to deal with straggler problem. He used a similar idea. We just set up a threshold. If you do the update within this threshold, you're selected for this round. Otherwise, you just wait for the next opportunity. It's very similar here, right? But I don't know, probably the way they pick up the threshold is different, but in general, it's, why do they use the idea? So
Oh, is it like they develop some theory and use that theory to guide their design, their algorithm design?
Yes, yes to both the questions. Yes, I know that this concept is not kind of new. They just add a couple of more things, but the main focus is that they can obtain a proper upper bound theoretically for this, and the theoretical analysis kind of guides the entire algorithm design and the working based on that.
okay.
And
This,
there is,
this delta is nothing related to the global clock setup, right?
yeah, I mean, actually, there is that one part that this paper does, that first they use this pre-specified global clock time, but they do not, I try to find, but they don't use this in theory. Instead, in the theory, they use another variable which is related to the global clock time. Instead of that, they are just saying the latest number of rounds within the clock time. And they use like rho kind of another parameter, and they use that for the analysis. They could have used the time itself, but maybe for better ease of the proof, maybe they use the latest rounds instead.
But first of all, I think intuitively they should be correlated. Second, um, I think for the global clock time, I don't know, it cannot avoid the starvation problem or straggler problem, yes, but starvation problem, say you want to guarantee certain client client I to participate at once within, delta rounds or something. You cannot do that, right? If you're always slow, probably you never ever have a chance to participate. If you set up a global clock time, with a reasonable value. If you set it very large, it's nothing different from, you don't set up anything. But if you set up with reasonable value, there's a possibility certain kind of stragglers, they never ever participate.
Yes, I agree with you. I read that.
Okay, anyway, you just move forward. Let's say what they have done, then probably we can do more discussions.
Okay. So this is on the server side. So continuing with what is the different thing that they do on the client side is first, the initialization of the local parameters remains the same. And the Y, which is maintained by the server, is also maintained by the client to say that this was the last update that I sent to the server in this particular iteration. And for the local iterations, we see that the local HDD step is computed, and let's say V is the update. And if the client is going to be communicating with the server in this given round, like I said, the main assumption is the computation happens in parallel with every client, but the communication may or may not happen in that round. So in this given round, if the client is going to participate, which means that he belongs to this set CT+1 was only for representation purpose, they put this in the algorithm just for better understanding. So the idea is just to know whether the client is participating in this round or not. So if he is going to communicate with the server in this round, then he will set the model update, the VT+1 minus the YT, which was the latest update, which was maintained by the client that he sent previously. He takes a difference between that and sends the delta to the cloud, to the server. And then the server does the global aggregation, and then the client receives the XT+1, and then he continues to the training. So just only one part is the additional thing that they do, that if the client participated in this round, he sends the update. So he receives the global model update from the server. So he updates his local copy of the update. And then he also updates the YT+1 because he wants to maintain the copy of which was the latest update that was received by him. If the client is not participating in a given round, then the XT is still updated with its own update, the VT+1, and the previously received YT becomes the YT in this round, is what he updates. So the case when the client is not participating in the given round, he still can be updating his own X and Y, his own model parameters, so that in the next round of training, when he decides to participate or when he has enough resources to be able to participate in the training, he can use the latest parameters that he had to continue the training. So this paper shows that by doing this one small step, the convergence can be improved, and also that they'll be able to achieve the same results as the synchronous or the normal way of federated learning. So this is the other extra thing that they do.
If there is something wrong here in the algorithm for the local SGD step, looks like they are only doing one, they just perform one step of SGD, right?
Yes, actually, I've noticed that too. In the algorithm, they're only showing that. But in the explanation, they say that they can use a mini batch SGD and do several rounds of local iterations. And you can set the value for the local iterations as you wish. But they have not shown that part in this algorithm. They just show as if it is just one round of SGD.
Oh, okay, okay, I see.
Yeah, yeah.
So here, how can, each device to decide if they're, justify, I don't know, how can each device to tell, they belong to say T+1 or not? The CT+1 is determined by the global clock time, or is, just like Dr. Guo asked, is selected by certain kind of criteria, or just decided by the edge server? How can each device to tell that?
So Dr. Ban, like the CT+1 is like just some kind of an assumption, kind of a set, which really does not. It is only to see if this client is going to participate or not. So for your question, let's say in this particular round, so let's say round T, the client, let's say after he does a training, but he may not be able to communicate because he lost the Wi-Fi connection. So he will not be able to communicate. So in that case, he goes to the else part and he just updates whatever he computed, the VT plus 1 as the XT plus 1. And then he waits until maybe he gets the Wi-Fi connection back. And in that round, he will try to send the update that he kept computing locally. So the main scenario that matches this kind of situation is, yeah, probably the client is still able to do the local computations. Maybe he's not powered off or anything, but just that he cannot do the communication because of the Wi-Fi issue or some other problem has happened. So only the communication is arbitrary. So that's how the client participation in that round is determined or not. This set CT plus 1 is really like superficial. It's just to show in the algorithm, they just wrote this.
Okay, so it's more like kind of conceptual definition of the C set, right? It's not like
Yes.
Mathematical definition. Okay.
Correct. You're right. So yeah, these are the kind of small extra things that they do in this paper, which they show theoretically that leads to very, very better results. So this was the algorithm. Next, I will show the effect of delta that they emphasize. So delta is the maximum gap that can happen between two communications of one single client. Or you can think of this as a maximum delay. This is like the maximum threshold that you set between the communications. So in this asynchronous paper, they show that it is very important to have an upper bound for this. They say that if you do not have an upper bound, then the convergence may be difficult. And they show that this delta is able to help them to achieve tighter convergence results. And they show that for both strongly convex and non-convex functions that they derive how we can set the value of delta. And here for the strongly convex function scenario, they say that if we set this threshold to be a function of O of root T by N, where N being the number of clients and T being the total number of rounds, they say that they can reach the same convergence rate as the normal mini batch SGD with communication happening synchronously for every round. And in the non-convex scenario, they show that if you set the delta value to be a function of the fourth root of T over N, then they're able to reach the same convergence rate as the mini batch SGD. So I think their contribution is more from the theoretical aspect to show how this design can be guided better. And next, I'll talk about the theoretical analysis. They have really deep explanations and proof for the theorems that they propose. I am just going to highlight the main theorem that they have, where this is for the strongly convex setting, and WT can be decided as a weight, which is nothing but the delta, which is a threshold that was set, plus the current iteration, the square of that. Using this, we have a summation of that is a parameter called ST, which is also a variable that determines the convergence. And we see that after T rounds of running this algorithm and using a particular learning rate, they are able to achieve this kind of a convergence. And here, if we see the result, we see that this last term has much better dependence on the delta square. They compare it with several other asynchronous communication federated learning papers, where the best paper amongst that achieves a delta power 4. And this paper is achieving delta square. So the dependence on this delta is also kind of reducing. And as a consequence of that, the bound can be improved for the delta. So like how we saw in this case that we can set a root T by 1. Yeah, so more like where most papers have the fourth root of T over N, this paper is only leading to the square of T by N. So that way the bound is also getting improved, more tighter, and the dependence is also kind of reduced. So this was for the strongly convex functions. And they have a similar kind of analysis for the non-convex settings, where in the non-convex settings, they use some if max. It's a term just to say that what was the first x0 function that you started with to the global minimizer x star. As a difference of that can be seen as the f max. And after running the complete t number of runs and using the learning rate or the step size in a particular range, we obtain a result like this. This again shows a great improvement, like this particular term where we see the grade G max as a gradient. So we see that the dependence is again reduced from the delta power 4. We are reduced it to delta square. And again, this has a direct impact on the total convergence, that the delta bound is reduced, where most papers have the 8th root of t over n cube. This has a 4th root of t over n cube. So the bound again has gotten tighter. So this was the main overview of the theoretical analysis that they provide that I wanted to show.
So the delta here
Mm-hmm.
Is an assumption, right? So you assume that every client will participate at least once every delta runs, right?
Yes, this is the assumption, right?
Okay. So what's the assumption behind each client? I mean, for example, what's the assumption behind the CT there? Assume that according to the algorithm, the CT well depends on your assumption about each client's computation capability, right? Some of them, they are very slow, some of them they're very quick. So I assume that you have to, for example, do you assume that all of them followed, for example, exponential distribution in their computation time, or follow a Gauss distribution, things like that? Without assumption, I assume that without assumption, it's impossible for you to derive an algorithm like this, right? So what's their assumption? Do they have an assumption there? Or they only need an assumption like the delta here? Because this delta is very, this assumption is very weak. It's not a very strong assumption. They don't contain a lot of information.
Okay. Yes. Okay. I understand your question. So firstly, the CT and the delta, the difference would be that the CT was dependent on the T, the current iteration T. So it's just saying that in my given round, who is able to communicate with me or not. And the second assumption about the clients that you were asking is, they assume that all the clients have a synchronous kind of a computation. They all perform the same number of rounds. They all take the same number of steps. They all have the same number of local iterations, and about the computation, they assume that all the computations happen in a similar manner of all the clients. So that's why the difference comes only in the communication part, which is why they're able to use only the delta part. If they had not assumed this kind of a computation assumption, maybe this delta would not be enough, as you just pointed out. You might have needed something else. Yeah.
So you mean that they don't consider computation heterogeneity, they only consider communication heterogeneity?
They do consider the computation heterogeneity, but they assume that the assumption is maybe not very practical, but they assume that all the computation happens in a synchronized fashion. But just that the communication is not asynchronous. Yeah.
Yeah.
Yeah, your question is completely valid. I know that if you have heterogeneous clients, then the computation time is not the same for everyone. That's exactly, I totally understand that.
Yeah, what I mean, can you just go back to the assumption? In the very beginning, you talk about the assumption, right? About this paper, I think it's go to the, this one.
Yeah.
So, that, well, takes the same number of step per unit of time. So the first assumption, each client takes the same number of steps per unit of time. So what does that mean? It means that their computation speed is almost the same. Is that what they mean?
Yes, exactly. So yeah, it's like, I think even in like most of the experiments that we see is when we talk about the local computation and global communication, the times, we say that the overall training may take a lot of time, but if you were only to consider one mini step, one mini batch step, or one single iteration over one client, it is very small and it will actually kind of be very similar to most of the other devices. Like the single step, the very small iteration that you take per unit time, that will usually be kind of same. I think we found it to be some milliseconds for different types of data and different types of model.
Okay. So they just so that they don't consider computation heterogeneity. So for the communication, they only assume that each client, you know, and every round there are random as number of client, you know, sending their update to the server. However, they are required to participate at least once in delta round. Okay.
Yes, I think more they do say that the clients can be heterogeneous and the data distributions can be different amongst them, but they only impose this assumption for the number of steps per time, that to be according to the global clock, and that will be kind of in synchronous for all the clients. But I somehow feel that the point that you mentioned is what I had on my mind also, that if you look at the overall number of local iterations, like each of them are taking 10 steps. So that 10 steps may not be the same time for all of the clients.
Yeah.
Some clients may be faster, sometimes may be bit slower. So if you set the global clock and the server expects the updates to return to him by then, so it will not just be dependent on communication. I think the local computation also plays a role, but this paper is not highlighting on that part. It only highlights this communication part.
Yeah, okay, I get the point.
After the theoretical analysis, I would next have the experimental section. If you have any questions, please feel free to stop me. Because this paper has just some updated methodology than federated averaging, they consider a different kind of baseline settings, which I'll explain later. First of all, they do the experiments on 3 data sets, the MNIST, Fashion MNIST, and the Cypher-10. And for all these data sets, the common thing we see is they all have 10 classes, and they are using simulation. They do not use an on-device platform training. They just use a simulation, and they have 10 clients, and they split the data in such a way that each client gets 1 class. And then they define a mixing rate, mu. This mu measures how identical the data distributions are across the different clients. So for each client, they kind of divide it in such a way that they see that 1 minus mu fraction of data is selected from the class corresponding to the same client. And they take mu fraction selected from any random class amongst the remaining 9 classes. So this way they have like a mix and match kind of data to see how a non-identically distributed data can have impact on the performance. And likewise, as we can see, if mu equals 1, which means that this fraction becomes 0, which means that all data have all the clients have all the data which is identically distributed. And if mu equal to 0, it means that the client is only holding data corresponding to his own class. He does not have a mixture of the classes from the other clients. So this is one part. Then for the models, they use 3 different kind of models. For MNIST and Fashion MNIST, they're using a very small neural network of just 1 layer and softmax activation. And they perform the mini batch gradient descent with a batch size of 20. And for Cypher-10, they use 2 kind of neural networks. One is a shallow convolutional neural network with 3 convolution layers, ZigBee activation, max pool, and then 2 followed by 2 dense layers, also with ReLU and softmax. And they do the evaluations on a second network, which is a more standard, deeper CNN, which is the ResNet34. And for the baselines, they have 4. One is the synchronous local SGD, which means that after every after the local iterations, every client is sending the update to the server, which can be thought of as the full SGD. And this is in the graph, we see it as full SGD of delta. And the second is the round robin, where you, for any delta number of rounds, you say that k number of clients will participate in this round. Then you would say the remaining k plus 1 to 2k, then so on. So it's like a round robin circular fashion. Then the third baseline is the random communication, just like federated averaging, where the server will select a random number of clients, like a subset of clients, like maybe the CT plus 1 in the federated averaging kind of case. This is denoted by random. And the last one is the imbalanced communication, where we say that client I communicates every I rounds. So if client number 2 will communicate after 2 rounds, client number 10 will communicate after 10 rounds. So it is a very imbalanced but predetermined way of communicating. So in these 4, if you see, the round robin or the imbalanced communication kind of is the asynchronous communication, what this paper talks about. So the comparison goes with these things. Talking about the evaluation, first we see that this is an experiment by changing the mixing rate. The mixing rate was mu. By changing this mixing rate and seeing how non-IID the data can be. The 3 graphs represent the 3 data sets. So the first one would be the MNIST, second would be the fashion MNIST, the third would be the Cypher 10. And on the axis, you have the total communication coming from clients, or the total number of updates that goes from the client, and the accuracy on the left. And the round robin can be seen as this paper's method. The random can be seen more as the federated averaging, and the full SG is the normal SGD. And again, the round robin, they've changed the values of delta, and they're trying to compare what happens with the changes. So like, as we see, setting the delta to be a higher number, for example, 5 over here, we say that the accuracy is much better, though we do not communicate so often. But as you change the delta to be a lower value, which means the expectation is the client is going to participate more often, we see that a lot more communication will be needed from the client, but the test accuracy is not reaching so fast as the convergence is slower. So if we were to extend this 250 like beyond the 250 and we keep going, then we see that all of these will converge eventually, but just that this one is much slower. But the asynchronous method is kind of way faster compared to the other ones. And we can see a kind of similar behavior when it comes to the changing the mixing rate. Here they've changed the mixing rate to half to make the distribution more different. So this case is more of the identical. This is the more non-IID kind of a scenario. Here again, we see that the asynchronous shows better performance compared to the synchronous versions. And for Cypher 10, we see that the communication, the convergence is much slower, as we know. So that's why this looks way bad. And if you look at the brown line, which is the full SGD, which is doing local iteration and then communicating per round, we see that the performance, especially when it comes to a bigger data set like Cypher 10, the performance is actually much worse compared to the other ones. And I just extended this to, there were several other figures. I just put the other one, which is the mixing rate of 0, showing that there is a lot way different kind of data. Here we see that the full synchronous update of all the clients to the server is kind of unnecessary, because if the data, as long as the local data distributions are not completed disjoint, we may be able to achieve some very good accuracy compared to the others. So this is the other small thing that this paper mentions, that how disjoint the local data distributions are, or how different they are. So if they're very different, then we see that the performance is kind of not very good. And the second experiment they do is by weighting the mu over Cypher 10 for the deep neural network, which is the ResNet 34. Here they're using the imbalanced communication and the random ones and the full SGD. Here, by looking at the result, we can see that if you have a full synchronous update of all the clients to the server, it becomes very unnecessary, irrespective of any model architecture. So we do not really need to synchronously update at every iteration. They show that even other ways we are able to get some better results. And discussing about the results that we just saw, first we'll talk about the synchronous versus asynchronous. What was the difference? Full SGD, which is our synchronous, with delta equal to 1, has the largest communication cost per round, as we saw. And compared to the methods that this paper has, they are reducing the communication per round by 1/5 or 1/25 times. And the communication that they achieve is like 80 to 81% of accuracy compared to the others. And talking about the role of delta, which is the more highlight of this paper, they see that the full STD or the round robin or the random have kind of similar communication requirements, but the random has slightly outperformed by the others. And for imbalanced communication, they show that while the communication gap is just 10, the average communication per round is reduced by a factor of about 3.5. And the accuracy of random in the figure we saw was like very fluctuating. That is because the random really does not guarantee the same clients are selected every time and whether the distribution is the same or not. And they also discuss about the role of the IID or the non-IID, how heterogeneous the data of the client is. And the difference between the cases we see where mu equal to 1 or mu equal to half is very minor. So when it comes to more identical kind of data, if you reduce the fraction of difference by a little, then there is not a lot of difference in the accuracy. But as you keep changing and as you keep decreasing mu to make it more non-IID, we see that there is a 3% drop in accuracy for smaller data sets like MNIST and 11% drop of accuracy for bigger data sets like CIFAR-10.
Can you just explain what mu is? I'm not sure if you explained it earlier, but I missed that part.
Okay, I'll come back to it. Okay. Mu is the mixing rate that was used to determine how identical the data distributions are across the different clients. So in their experiments, they're choosing the mu in such a way that 1 minus mu fraction of the data is selected from the class of that client, and mu fraction of the data is selected from any random class. So if you see that if you make the mu equal to 1, it means that the data for all the clients are almost identically distributed. So it is more of the IID case. And the other extreme, if you make mu equal to 0, which means that the client holds data only corresponding to its own class, which means it's highly non-IID. So that mu
what
is
do
like
you mean by each client only hold data corresponding to its class? Because in this data set, the clients and the class, they are not identical, right? Like for MNIST, you have classes from 0 to 9. But for clients, if mu equals to 0, do you mean like each client only had one class? Like each client only?
Okay. So first, they chose these data sets because they all have 10 classes, and they're only using 10 clients for the simulation, such that every client is associated with one class. Like client 1 gets class 1, client 2 gets class 2. They first initially do this kind of division.
But in this case, if mu equals to 0, it means each client only have one class, right? And if mu equals to 1, then it means mu fraction is selected from the random class. So each client still has one class, right? So each client, they either have, like, for example, if you have from 0 to 9 labels, then each client, in the IID case, each client only has, you have 10 clients, then each client have like at 0, 1, 2, 3 to 9. And if you, in the no IID case, when mu equals to, so I think like the, do you get my point? So the last, the definition, like in this slide, for each client, 1 minus mu fraction of data is selected from the class corresponding to the client, while mu fraction is selected from the random class, actually contradicts to your ID description. Did you get this from the paper, or did you summarize it yourself?
I got this from the paper, Professor.
So so can you explain how this could be IID? Because I don't think if mu equals to 0, or if mu equals to 1, then each user still have only one class, right? How can this be IID?
I think what they mean. I think what they mean is that so they say mu fraction is selected for a random class. I think what they mean is that if you mu equal to 1, that means that all your examples will be randomly selected from the overall data set, 10 classes, right? Each example is randomly selected for one of the classes.
Okay, I got it.
I think that's what they mean, but their description is not very accurate. So
Yeah,
that's
it's very misleading. Yeah.
Yeah.
So
yeah.
this is basically like if it is no IID, then a portion of the data are randomly selected, and a portion of the data only has one label, right?
I have one question. If mu equals 1, did the distribution is really IID because mu fraction is selected from a random class? This random class is means, for example, for the first collect, maybe we select the class 1 and a random class is from another one. For example, from 2 to 10 or 2 to 9. So this random class is this random class include the corresponding class itself.
I think I'm not sure what your question is. So are you asking about the IID case or no IID case?
I'm asking the IID case.
So in the IID case, mu equals to 1, right? Then you basically is like all the data are selected from the random class. This is basically what I asked just now. So, and we just explained like, it is not like you have all your data is selected from one random class. It's basically each sample is assigned a random label. So does that answer your question?
Okay, so assume we have 10 class and 10 clients, and now for the class for the client 0 and the corresponding label, it is class, so it is 0, and we will select 1 minus u fraction, so it is 0, and from 1 to 9, so it is from so this is a random class. We select from 1 to 9 or from 0 to 9.
I think it should be from 0 to 9. Because they just say random class.
Okay. So I have yeah, it's clear now.
Okay.
Okay, thank you.
By the way, so for the data for the experiment setting, so I think that now looks like the key parameter is delta, right, in the algorithm, and in their simulation, how do they, if I choose different delta, how can I simulate this case? I mean, for example, if you say delta equal to 5, that basically means that each client will participate at least once per 5 rounds, right? So how do they simulate this asynchronous communication case in the experiment, I mean?
Okay, so for let's say the delta equal to 5, then randomly certain number of clients will only send update for aggregation at round number 5.
Each round you have some client participating, right?
Yes. So each round there are some number of clients. Yeah. That is like.
Yeah. So do you mean, for example, okay, so let's say in this way, you have 10 clients. Now you assume the delta equal to 5. Then do you mean that each round you will select 2 clients to participate? For example, the first round is 1, 2, second round is 2, 3. So
Okay.
I mean, that will have a huge impact on the performance of the algorithm.
I think Dr. Gore's question is,
Yeah.
how do you model the participation willingness, just in case, I mean, during each round, there are multiple users that are qualified. So all these users are going to submit that, or those users are going to have any kind of a consideration or something, but just in simulation, how do they do that?
Okay. Yeah. So for example, in this case, where you have 2,5, 5 means the fifth round is when all the clients are going to send the update, and 2 corresponds to how many clients are going to participate. So they kind of choose this set like 2,5 or 3,6 or things like that. And amongst who is going to participate in one round would be random. And for round number 5, like let's say delta is 5, then all the clients are going to send the update. So for the other times when delta is not 5, which is less than 5, for example, or more than that, then it's only the number of clients. For if I set it as 2, then it is going to be a random selection in the simulation part.
Yeah, so this will be, do you know the round robin, the selection? I mean, the round robin is basically like, for example, 1, 2, 3, 4, 5, 6 to 9, 8 to 10. So you first select the first 2, the next round you select the third and the fourth. Then this is more like a round robin, is more like a circle, like a circle. You know, you choose the client in a circular way. So, for example, for this RR25, so 2 basically means each round you are select 2, right? And 5, I assume 5 basically means each client must be selected within 5 rounds, right? So this, correct. If you say this one is more like a 2-5, it's basically like, okay, I will select the first round 1, 2, second round 3, 4. So this is, I mean, this is should be very similar to random selection in Federated averaging. Because for the averaging, right, you can also say, okay, I'm going to select the client, you know, 2 out of 10 clients in each round randomly. You know, in this randomly, you can choose a round robin random selection. They will give you the same 2, 5. Mm-hmm. I mean, so why your algorithm can outperform for the averaging using the random selection?
Okay, so for that, let's say it's the same thing that we are for, let's say the delta was set as 5 and we selected 2 of them in a round robin fashion. But in federated averaging, what happens is you have this fact that at the 5th round, every device has to participate. That compulsion won't be there in federated averaging because every time you're just selecting 2 clients randomly for every round. Yes. And in this round, in this, that will be different. So this adds to the better performance.
So okay, I kind of get at one point. It basically means that you mean that in federated averaging, because I will only select 2 clients per round. So in each round, only 2 clients will update the model, will perform the local SGD, and then update the model. But in their algorithm, looks like even you only have 2 clients that will participate or will communicate, but all clients will compute their update. Is that right?
Yes, exactly. And I wanted to add that through this algorithm as well. So if this was the federated averaging case, let's say in this round, the client did not participate at all. So he did not send the update to the server. So he does not do any kind of local training. So this else part does not remain. So whatever he has will be a very old update from the server that he received long back.
Yeah. But you know, then the comparison is not fair. You know, because you know it's basically like the federated averaging. You only have 2 clients which will participate and contribute. Now in your algorithm, in each round, you actually have 10 clients which will contribute. They keep updating, right? But the
Yes,
only thing is
yes.
that they didn't transmit.
Yeah.
So if you only compare that communication cost, of course, your algorithm will be better than Fed averaging with sampling, because you have more you have more computation.
Yes.
But if you talk about, for example, if you consider both communication and computation, this may not be the case. And also, sometimes, most of the time, it's not because we cannot communicate. It's because we are not available, some client, right? You are not available, so you don't have time, or you don't have spare resource to participate in federated learning, not not only for communication, but also for computation.
Yes. Yes. Exactly.
So,
like.
Yeah, so that's why I'm saying, well, it looks like their comparison is not very fair if you think about how they achieve higher communication efficiency. Just because, well, I ask you, okay, so even if you don't participate in this round, you just keep updating, then hopefully one day your update will be used by the server.
Yes, that's the concept. Yeah, that is what is guaranteeing better performance. Yeah.
Yeah, I'm not sure whether that's true or not, but looks like what they do is they don't really. I didn't say why their algorithm is better than Fed averaging with random sampling, because communication cost is just one part, but you have more computation cost, right?
Yes.
So unless you can prove that adding those two together, your performance is better, otherwise, your requirement is stronger, because you assume that every client, you must always update your model, no matter whether you communicate in this round or not.
Yeah.
I don't know. You can if you say if you say, I'm not sure whether they have the open view comments. If they have the open review comments, you can check their comments to see whether other review have the same problem or not. Because I know this paper actually, they have been rejected by a lot of conferences, and then finally they get through in ICML. So there must be some reason there. This paper, it was first posted to the archive for, I think it's kind of almost 1 year ago, and they keep rejecting by different conferences.
I think their basic assumption, like you said, Dr. Guo, is communication probably is a bottleneck, but computing resources is not the bottleneck. You can always do the computing. You can always do the local training, keep update. You wait until, for example, certain time your channel is available, then you do the global updates. You do the local updates to the server. Then, you enjoy the diversity from other users from the server. So yeah, I think probably that's the basic assumption. I agree with you. I think probably computing in terms of engineering point of view, in terms of power consumption, in terms of delay, latency, probably is more dominant than the wireless communication. In case there is enough bandwidth available. Okay, I think the paper only works for the case that there's not enough bandwidth available. Right, so, but for the local device, they have enough power and computing capability to do the training stuff, right? Oh, by the way, Pavana, are you finished? So can I stop recording and we can do more discussion afterwards?
I just have the conclusion slide, Dr. Pan.
Okay, you just quickly finish that, and then I'm gonna stop recording.
Okay. So in conclusion, we saw that if we can significantly relax the communication requirements on the clients to capture some practical scenarios, we can still be able to achieve some standard convergence rates in the federated learning setting. And the communication gap, the delta we were talking about, if it is unbounded, then the learning algorithms can easily diverge. So it is better to kind of have some bounds for it and use that, which will help us to achieve better convergence rates. And through experiments, it was observed that any deviation from the global data distribution is a very important parameter that affects the performance. And the main result shows that for both the strongly convex and the non-convex functions, we were able to achieve the convergence rates that match the synchronous version. So that's all I have. Thank you so much for listening.